In this problem, your car starts from rest and you step on the accelerator. After 10 seconds, you're going 20 meters per second. Assume the clock starts the instant you hit the gas pedal, and assume the acceleration of the car is constant once that gas pedal is pressed. First, we'll create a motion map representing the situation. Now we're going to start off with a dot that has no arrow because we're at rest. And that would be at t equals 0, the start of the clock. Now as time goes on, we're going to hit the gas, and that's going to cause us to accelerate. So we want the spacing between the dots to get larger and larger. We also want to give arrows, which are increasing in size as time goes on, showing that the car is speeding up. Alright, that's a good motion map for this situation. Now we're going to draw some qualitative motion graphs. On the next page, we'll do it quantitatively, meaning with numbers. But for now, we just want to know what kind of curves we're expecting to see in those graphs. So first of all, notice how the velocity is increasing with time. And it also starts at 0. So we want to start our velocity at 0 in this graph. Over time, it's going to increase. And if we have constant acceleration, it'll increase in a nice linear fashion. Now the acceleration is the slope of the graph above, so we expect that that will be a nice horizontal straight line. It's constant acceleration. And then, as we showed in previous videos, the type of curve we'll expect to see here will be a parabola. That's what we want to see when we make our motion graphs quantitatively on the next page. Alright, let's try it. We'll use the same numbers as on the previous page, so after 10 seconds, our car is going to be going 20 meters per second. So let's let our velocity be 0 at time 0, and let's let it jump up to 20 meters per second after 10 seconds. Now we just want to connect those dots, and that's going to be our velocity graph. Notice here they say the initial position of the car is actually going to be 100 meters. That would mean we'll start our car off right here at t equals 0. And we expect it'll have a parabolic increase of some kind after that. Now let's go ahead and graph the acceleration. Now how do we find acceleration for a situation like this? There's a formula for it. The acceleration is going to be the change in velocity over time. So our acceleration is going to be v final minus v initial over t final minus t initial. Our final velocity is 20 meters per second. We started at 0 meters per second, and it took us 10 seconds. This is an acceleration of 2 meters per second. But another way of writing that would be simply meters per second squared. Now that we have this value, this acceleration value, we can go in and sketch that. All right, next, for this question, it says, let t equals 0 be the initial time. Choose a final time of tf equals 10 seconds. We want to shade the area underneath the acceleration curve, which is between t equals 0 and t equals 10. So now we're going to find this area. Now that area has meaning in physics. Notice, for example, that the width of this rectangle could be considered delta t, and the height of it is the acceleration. Now what do you get if you multiply an acceleration times a time? Well, according to the formula, delta v equals acceleration times time, this would produce a change in velocity. And so that is the meaning of the area under the acceleration curve. It's the change in velocity of the graph above. So what do we get if we multiply them? Well, first, let's be very clear about what our interval is. We want to go from t equals 0 to 10. We want to multiply our acceleration, 2 meters per second squared times the time of 10 seconds. And that tells us that our change in velocity should be 20 meters per second. And this is in agreement with what we see here. The height of this side of the graph is 20 meters per second. Oh, and let's draw that. Delta V. So the idea here is that the area under one of the curves is equal to the change in value of the graph above. And just like the area under this curve equals the change in value of the graph above, the area under the velocity curve is going to have meaning as well. It will be the change in the position graph above itself. And that's what our next question asks. On your v versus t graph, shade the area underneath the velocity from t equals 0 to t equals 10. The signed area under the velocity curve will correspond to the change in position from t equals 0 to t equals 10. Use the area of a triangle formula, delta x equals 1/2 at squared. So normally area of a triangle would be 1/2 base times height. But what is the base here? It's delta t, or elapsed time. And then our delta v is simply at. So 1/2 at times t. So we get 1/2 delta v times t is going to be 1/2 at squared. And that's the formula we can use now to find the area of that triangle. So let's try it here. Delta x from t equals 0 to 10 will be 1/2 2 meters per second squared, 10 seconds squared. All right, let's see what that gives us. That's going to be 100. 100 meters. All right, now we can go back to the position graph. We can go over 10 seconds, and then we want to go up 100 meters. That'll take us to the final location for this vehicle. All right, we can also fill in some of these things down here. When no time has elapsed, you haven't gone anywhere yet, but after 10 seconds has elapsed, apparently according to our equation, we've traveled 100 meters. Our position will start off at 100, and it'll grow to 200. But now the question becomes, what happens in between? It's not going to be just a linear growth this time. It's going to be parabolic. So we want a formula which will give us the displacement of the car. And that's just going to be simply delta x equals 1/2 times 2 times t squared, which is basically just going to be t squared. So now we can go through and fill in all our displacements. It's going to be 0 squared, then 2 squared, 4 squared, 6 squared, 8 squared, and 10 squared. All right, now we'd like to find a formula for the position of the car. All right, so we could start with the delta x equals 1/2 at squared. Then I would break it into xf minus xi equals 1/2 at squared. Now we want to move our xi over to the other side. We're going to get x equals 1/2 at squared plus xi. That's going to be our formula. Let's see if we can plug some things in though. We'll get t squared plus 100. That's going to give us the position of the car throughout time. All right, so we're looking at 104 meters, 116 meters, 136, and 164. Now we can plot. And we'll connect our dots as best we can. And there we have it. We constructed a quantitative position versus time graph for an accelerating car.